Alright everyone, welcome back to another episode of From the Rails Up. This time we're going to be talking about trucks. Specifically, we'll be going over what they are, what they do, the parts of a truck assembly, the periodic maintenance and wear limits on truck assembly parts, and everyone's favorite, some FRA rules. I can already tell that this video is going to be a long one, so we'll just get right into it. How'd you like that transition? Hopefully you did, because you're going to see it like 5 times in this video. Anyway, first things first, what are trucks? Well, for a short definition, a truck in railway terminology is a chassis or framework under a piece of rolling stock to which the wheel sets are attached via bearings. I'll throw in here that in much of the rest of the world, what we in the United States would call a truck is referred to as a bogie. They're different words for the same thing. Since this series is going over SD40-2s, I'll be sticking mostly to the General Motors HTC truck design. The HT in HTC stands for high traction and refers to the adhesion characteristics of the truck. I'll talk about that a little bit later. And the C in HTC stems from the AAR's wheel arrangement classification. This system uses letters, numbers, and dashes to refer to numbers of powered and unpowered axles and to separate the trucks. For example, an old EMDE unit like this, which I think I've showed before, has an A1A, A1A wheel arrangement. The dash means that there are 2 trucks, and the A1A means that each truck consists of a powered axle, an idler axle, and another powered axle. The AAR classification of an SD40-2 and most GEES44C4 most 6-axle locomotives is CC, meaning it has 2 trucks, each with 3 powered axles. There are plenty of other truck designs out there, Bloomberg, Alco, Flex Coils, and the list goes on. But for the sake of not rambling any longer than this video is already going to be, we'll just stick with the HTC trucks used on Dash 2s. It also bears mentioning that, at least for EMD trucks, most of the parts that go into an HTC truck are the same. Pretty much every EMD truck I've ever seen uses the same spring pack and that kind of stuff on the traction motors. We'll get into that later. Anyway, now that we know what a truck is, let's talk about what exactly it is that they do. Before we get into exactly what trucks do, I'd like to make a comparison for you guys. This is a GP40. Ready to operate, it weighs in the neighborhood of 250,000 pounds. This is a Bloomberg truck that goes underneath of a GP40. Alright, now this is a covered hopper, a type of freight car. Fully loaded, this one can weigh up to 268,000 pounds. This is the truck that's underneath that freight car. Look how much lighter this truck is compared to the truck under the locomotive, even though the freight car is heavier. This is not only done because, a light truck on a car means the car weighs less so you can get more payload, but mainly because freight car trucks do not have traction motors and all the associated forces that come with that. So now on to what they do. Obviously, trucks are a very crucial part of any piece of rolling stock, and chief among their functions is suspension. With everything else that trucks do, suspension is of particular importance because that is what keeps everything on the rail. I don't think I need to explain why staying on the rail is very important. The suspension on a locomotive is broken into primary and secondary parts. The primary suspension consists of the springs above the journal boxes that support the truck frame on the wheel sets. This part of the system is responsible for keeping the wheels in contact with the rail over any kind of irregularities, as well as absorbing road shocks imparted to the wheels. The secondary suspension, specifically on an HTC truck, consists of 4 rubber spring pads under the corners of the bolster. The secondary suspension distributes the weight of the locomotive through the bolster to the truck frame. It also allows for slight movement between the car body of the locomotive and the truck frame and provides another layer of isolation for the car body from road shocks. Speaking of the car body moving relative to the truck, there are also two side bearings that we'll talk about later on each side. These side bearings limit slightly the side-to-side roll of the car body. The second major function of trucks is to transfer the driving and braking forces from the locomotive to the rails. These forces are transmitted from the rails up through the wheel sets into the journal boxes, are absorbed by the truck frame, then go onward through the bolster and into the car body. These trucks also contain brake rigging and traction motors, and as such have to be able to absorb all of the internal forces created during braking and acceleration. For example, the brake rigging pressing against the wheels to create friction and slow the train down, and the reaction forces from the traction motors as they try and turn the wheels. We'll come back to this in a bit. As a bit of an aside, the reaction forces from the traction motors are actually part of what makes the HTC trucks have good adhesion characteristics. Since all the motors face the same way, the forces created by them all act in unison instead of some of them opposing each other. You don't have one motor pulling down on the truck frame and the other two trying to lift it. When that happens, you can get one wheel to have less downforce on it, and thus you lose some adhesion on that wheel. Speaking of downforce, this all also ties into suspension because braking and driving forces rely heavily on the wheels of the locomotive. Because braking and driving forces rely on the wheels of the locomotive being in contact with the rails and having sufficient downforce to have enough friction to transmit the acceleration and deceleration forces. Anyway, that was a bit of a tangent. We've got the forces from the rails into the truck. Now we have to get them from the truck to the car body of the locomotive. In order to do that, there is a giant pin that rests in the center bearing inside the bolster. I'll throw a picture of one of these up right here. This pin is also responsible for allowing the trucks to slew or pivot slightly under the car body of the locomotive so we can get around curves. So, in a sentence, locomotive trucks are responsible for providing suspension, transmitting driving and braking forces between the locomotive and the rails, and absorbing internal stresses created during driving and braking. So how do they do all that? Well, we'll get into components and see what they do and how they contribute to that. Alright, now that we know what trucks are and what they do for the locomotive, let's get into the parts of the truck assemblies that allow them to accomplish all the functions we just talked about. So, the first and largest component of a truck assembly is the truck frame itself. The truck frame is the component to which every other component we're going to talk about is going to be mounted. On an HTC truck, the truck frame consists of 6 sets of pedestal jaws joined together by 3 transoms. The pedestal jaws are steel members that descend from the truck frame and grasp the journal boxes on the ends of each wheel set. Within each set of pedestal jaws are a number of other components, including 2 double-coiled journal springs, 2 upper spring nests, a lower spring seat which contains the 2 lower spring nests, 4 shims between the springs and their respective nests, 2 nylon jaw liners, and a pedestal tie bar, which is sometimes referred to as a binder or a binder strap. The primary suspension consists of the double coil springs, lower spring seat, upper spring nests, and the shims. The upper spring nests are welded to the truck frame and hold one set of shims in the upper ends of the springs. The lower spring seat holds the bottom set of shims in the bottoms of the springs. The underside of the spring seat rests on a corresponding feature on the journal box, and that transfers the weight of the locomotive from the truck frame down to the journal box and by proxy into the wheel set. The shims between the spring seat and the springs themselves can be changed to compensate for different size wheels and to compensate for just general wear in the wheels. That's actually a subject we'll end up coming back to later in the FRA section. The other components in a set of pedestal jaws that aren't part of the primary suspension would be the jaw liners and the pedestal tie bar. The jaw liners are nylon pieces mounted to the pedestal jaws themselves, and they provide a wear surface between the movement of the journal boxes and the pedestal jaws due to the action of the primary suspension. The pedestal tie bar is bolted across the bottom opening of a set of pedestal jaws and is mainly responsible for transferring any driving and braking forces from one jaw to the other. Picture a wheel set and the journal box pressing against one jaw in a set of pedestal jaws to try and move the locomotive. If enough force was applied over enough time, you can imagine this would cause the bottom of the jaws to spread apart. It also bears mentioning that if the locomotive is equipped with single shoe brake rigging, the pedestal tie bars become crucial parts of the load carrying system. In a locomotive with single shoe brake rigging, the pedestal jaws have to absorb both the force that presses the brake shoe against the wheel and the force from the rail that's trying to slow the train down. As such, the tie bars serve the crucial role of transferring those forces from one jaw to the other in order to prevent that spreading of pedestal jaws that we talked about. The other major parts of a truck frame are the three transoms. These are the lateral members of the truck frame that hold the two sides of the frame together. They also play host to the traction motor nose suspensions. What are those for? Well, imagine trying to turn a wheel set in order to pull a train. Which is easier to move, a 20,000-ton freight train or a 5-ton traction motor? Obviously, it's a lot easier to move that traction motor than the entire train. As such, during application of power or dynamic braking, the torque from the pinions in the traction motors is going to tend to walk the pinion gear around the bowl gear rather than actually turn the wheel set. To deal with these forces, trucks contain a suspension system for the noses of the traction motors. The traction motor nose suspension pack, or spring packs, are mounted in a set of lugs on each truck frame transom. They consist of a stack of rubber springs and two wear plates or end blocks that are held together by two bolts. The spring packs are held in place in the transom by two guide pins, which themselves are held in place by a plate that is bolted across the underside of the guide pins called the guide pin keeper. These guide pins keep the spring pack from working itself out of position during operation. During installation and removal of the spring packs, shims of a specified thickness are used. These shims are installed between one end block on the spring pack and the bolts that hold the spring pack together. Note that the spring pack has to be compressed first in order for these shims to be installed. The shims will then hold the pack in its compressed state so that it's smaller than the space it sits in the truck frame and can then be slid out the side of the truck. Alright, so that's the major parts of the truck frame that went down to the combos. Now we'll go up to the car body through the bolster. The car body of the locomotive is supported on what's called the bolster of the truck assembly. The bolster is responsible for distributing the weight of the locomotive down onto the truck frame. It is also responsible for transmitting the driving and braking forces that we previously got into the truck frame into the car body. These forces are ultimately transferred to the car body through the center bearing inside the bolster. This bearing also allows the truck to slew or pivot underneath the locomotive. HTC trucks use a floating bolster design, and a floating bolster design uses some form of springs to support the bolster directly from the truck frame. Tangent time. The other main design for trucks is called a swing bolster design. Bloomberg and Alco trucks are two examples of these, as is this truck from under the E8 that we looked at earlier. Swing bolster trucks have a bolster that sits on a bundle of elliptical springs, usually they're elliptical springs, which are basically two sets of leaf springs on top of each other that sit on spring planks, which are hard to see in these pictures, but they're directly underneath the spring bundles themselves. The spring planks rest on a set of swing hangers that transfer the weight of the locomotive to the truck frame from the spring plank. As the locomotive enters a turn, the centrifugal effect will cause the car body to want to move towards the outside of the curve. The swing hangers will permit this motion, and as they do, they serve to raise the outside of the bolster, which will cause the locomotive's car body to lean towards the center of the curve. This will in turn create a restoring force that tries to return the car body to its centered position. I know that was a bit of a tangent, but that'll give you guys a little bit of context for some stuff that comes up later in the FRA section. Back to HTC trucks. HTC trucks have an H-type bolster, so named because it looks like a capital letter H. Big surprise. The bolster is supported on all four corners by rubber spring pads. These spring pads make up the secondary suspension and allow for some amount of vertical, lateral, and longitudinal movement of the bolster. Longitudinal movement of the bolster is limited by a set of 4 bolster chafing plates. These chafing plates are made up of phenolic resin and provide a replaceable wear part between the bolster and the truck frame. These chafing plates are also responsible for transmitting any driving and braking forces from the truck frame into the bolster. Anytime the locomotive is accelerating or decelerating, one pair of these plates is pressed against the bolster. While this is the case, any motion between the bolster and the truck frame will cause these plates to rub against the bolster, resulting in wear. That's the main reason for these wear plates being easy to replace. Anytime you're accelerating or braking, any movement of the secondary suspension is going to cause these to wear. But fortunately, they can actually be replaced without removal of the truck from the locomotive, which makes them easy to do. The last parts of the bolster have to do with the center bearing. The center bearing is the giant pin we talked about in the center of the truck. The center bearing, depending on the style in question, is made up of 2 halves that sit in the center casting of the bolster. The one I have modeled here is a newer style that I've seen. It comes in 2 halves, and there is a certain way that the split between them is supposed to face, and I, for the life of me, can't remember off the top of my head. I think it's supposed to be sideways. If I'm wrong, I'll ask someone that knows better than me. If I'm wrong, I'll correct that. Anyway, these bearing halves are lubricated by car oil, which is the same oil that we use in the support bearings in the journal boxes. They are lubricated by car oil that's added from a pipe that's located inside the car body of the locomotive. The oil is kept in and dust is kept out by a seal that goes around the top of the center casting, which seals against the underframe of the locomotive. So, that's all the major components of a truck assembly. There are also a few minor components I want to talk about, one being the shock absorbers mounted to both sides of the center axle on each truck. These shocks do the same thing as the shocks in your car. Mainly, they're there to dampen spring oscillations. They are also responsible for dampening the side-to-side rolling motion of the car body and the truck frame relative to the rail. As an aside, later model HTC trucks also have shock absorbers between the bolster and the truck frame to dampen lateral motion of the bolster. I'll throw up a picture here of one from an SD60M. There are also the guide bars for the brake rigging that I know I mentioned in the brake rigging video but didn't show. They're located between the pedestal jaws and interface with the brake guides on the rigging in order to keep the shoes aligned to the wheels. Also, speaking of brake rigging, all of those components are mounted to the truck frame in some capacity. And another thing that would be related to the brake rigging is the air manifold that actually supplies the air to the brake cylinders in order to actuate the brakes. And the last component I wanted to mention is the sand nozzles. Different locomotives have different sanding setups, but typically the sand nozzles are bolted to the underside of some of the pedestal tie bars. The sand nozzles are aimed to spray sand at the wheel, between the wheel and the rail, to increase traction. Post-editing here. One last thing I actually forgot to mention is some railroads use components called flange lubricators, which I'll throw up a picture of one here. These do exactly what the name suggests and lubricate the flanges with a block of graphite to reduce wear on the wheels. Alright, that was a lot of information. So, to go over it all again, and because I've received comments asking me to show actual components more, I'm going to throw in a video here of me going around an actual truck that's still under the locomotive, as well as possibly a truck frame, and pointing out some of the stuff we just went over. Post-editing me again, I actually got kind of lucky on this one. Remember earlier how I mentioned SD60Ms? Well, we just happened to have a foreign SD60M come into the shop as I was ready to start recording some of this, so I was able to get some footage from that locomotive, which will allow me to show you guys some stuff I couldn't on any of our engines. So yeah, enjoy. Alright guys, I threw a lot of information at you, so we'll go over it again here. I'm obviously recording this outside, and you can hear there's locomotives running around me, so you'll just have to forgive the background noise. But anyway, what we're looking at here is an HTC truck assembly, which you'll hear me refer to as a -2 truck that is underneath of an SD60M. This is not one of our locomotives. We do not have any of those. But you can see this is the same type of truck assembly that's under a true -2. You can even see right here, it's got GM HTC embossed into the truck frame. So anyway, we'll go over our truck components again. The first and biggest component we have is the truck frame itself, which you can see goes from down there, runs all the way around, jumps across, and then it looks the same on the other side. The truck frame is made of 6 of these, and this whole thing is a set of pedestal jaws. You can see there's 3 on this side, and then there'll be 3 on the other. There are also 3 of these lateral pieces that are called transoms. It's kind of hard to see in here because it's dark. Yeah, just like that. You can see there's a transom here. There is transom there, and there is a transom here. Those 3 transoms make up the lateral that joins the 2 sides of the truck frame together. And if we come back out here, you can zoom in on one of these sets of pedestal jaws. You can also note that this locomotive has GG bearings, which are roller bearings, and they're packed with grease and sealed. They are not Hyatt boxes like a lot of our locomotives have. But this component, it's not technically a journal box, but it does the exact same thing. So, inside of our set of pedestal jaws, you can see we have the primary suspension with the 2 double coil springs. We have the lower spring seat, which sits on the journal box. You can see we have these 2 shims that are not very happy in here. Then if you go up, let me turn the flash on again. And if you go up in there, can't really see it, but there's 2 more spring nests and 2 more shims up there. Back on the outside, we also have our pedestal jaw liners, if I can talk, which provide our wear surface as this journal box moves up and down. These allow that, these provide something for that to wear against instead of wearing against the truck frame. See, the jaw liners are held on by these 2 bolts, and I have actually seen these bolts back out and fall out before, and when that happens, you'll notice the jaw liner just drops down and sits on the pedestal tie bar. That's a bad day if that ever happens. Not a huge thing to fix, but still a pain. So we have, speaking of, down here we have our pedestal tie bar. See, this is just bolted directly into the underside of the pedestal jaws, and this pedestal tie bar holds the 2 jaws of the pedestal together. It keeps them from, like, if you picture this journal box pushing real hard this way against this jaw, you can imagine over time it trying to kick this jaw out. So that pedestal tie bar keeps those jaws from spreading. Now, if we go from the, thoughts evade me. If we go from the sets of pedestal jaws to the transoms, and you look down in here, you can see, let me turn the flash back on. You can see right there is your traction motor nose suspension, or your spring pack. You can see there's a set of lugs that stick out from the transom on the truck frame. And then the spring pack consists of the actual spring as well as 2 end blocks, and those end blocks each have a wear plate on them. The whole assembly is held together by these bolts right here, and it's kept in place in the truck frame by a pair of guide pins. You can kind of see the shiny up there, but those guide pins are held in place by that the guide pin keeper right here, which holds the guide pin up through the spring pack. Now that spring pack is this motor here, tries to turn the wheel
the motor nose is going to try to lift up or push down depending on the torque on the wheel. So that spring pack is there to absorb that force. Sometimes when these get worn out, you can actually feel, if you put the locomotive in a notch, you'll get a nice thunk as the slop in the suspension is taken up. Now you can see down here, where's my hand? Between, oh dang it, between that bolt head and the end block there's a gap. To remove that spring pack with the truck assembly out from under the locomotive, what you'll do is you'll lift up on this traction motor, and that'll compress that spring pack, and that allows you to fit a shim in there. And then whenever you take the tension off, that shim doesn't allow the spring pack to expand all the way. So now the spring pack is smaller than the gap it's in, and then you can just grab it with a hook and pull it out the side of the truck frame. That's how we remove those. But that's most of our components in here on the actual transoms. So now we'll go up to the bolster. This right here, yeah, I'll turn that back on. This right here is one side of the bolster, and this right here is the other. If you look, it's kind of hard to tell, but from here we go straight across. There's a piece in the center that connects them, and then here we go straight across again. That's how we get the H shape of the bolster. The bolster, you can see right there a hole in the bolster where the pin on the bolster spring pads sits. These are just rubber pads that are bolted to the truck frame, and then there's, as I mentioned, a pin in here that sticks into the bolster and holds the bolster in place. These spring pads make up the secondary suspension. They allow the bolster to bounce, shift side to side, and run fore and aft a little bit. There is also over here our phenolic resin, dang it, I lost it again. Our phenolic resin chafing plates for the bolster. So if you, let me back up a little bit. So if you imagine this locomotive is trying to accelerate, and well, I'll just go, yeah, if we're trying to accelerate and we're pushing the truck frame this way, you know, the wheel's going to push the truck frame into the pedestal jaw, and then that's going to push the truck frame into the bolster. That's going to shove, just like it is here, it's going to shove this wear plate against the bolster. So now any movement up and down, side to side, whatever, of the bolster is going to cause this plate to wear. And so these plates, there's actually just a number of bolts on the back side, and you can take those bolts out, slide the plate out, slide a new one in, and tighten it back up without having to remove the truck assembly. It's kind of nice. And then if we go right here on the bolster, you can see a lateral stop. This prevents the side-to-side movement of the bolster. It'll hit against this part of the truck frame to limit the sideways movement of the bolster. On the back side of the bolster, they are out here. Sorry, my hand was in the shot there. But on the back of the bolster, they're out here. If we jump up to the front of the bolster, you can see right down in there where the front lateral stops are. They do the same thing. They limit the side-to-side movement of the bolster. And you know, there's a wear part on the truck frame, and then there's the actual part on the bolster. While I'm up here and talking about the bolster, if I can find a good angle for it, you can see just about that block right there and the corresponding wear plate on the bolster. Those are what limit the amount of slew you can get out of the truck. So as the bolster, or as the locomotive enters a curve, the truck and the bolster are going to pivot to your left, and eventually that block on the frame will hit the wear plate on the bolster, and that limits how much slewing motion you can get in that truck. Them blocks are giant and welded to the underframe, like you can see. Also, while we're in here, you can see the center casting. It's a gigantic pin, which I think I threw a picture of up earlier. That giant pin sits down in there, and it's actually recessed up into the frame there, and then there's a seal and everything. Fortunately, we don't have a bolster sitting out where I can actually get a picture of this for you guys. If I get lucky while I'm editing some of this together, I'll throw one in here. But yeah, another thing of note on the bolster are these. These are called side bearings. You can see there's a little bit of a gap here. Let me get better grip. You can see there's a little bit of a gap here. The amount of space in that gap is actually an there's an FRA rule about that. Sorry, my hand was in the shot again. But these are called your side bearings, and the clearance here is very important. Too high or too low and we have issues. But there's a side bearing on each corner of the bolster on these HTC truck assemblies. Another component not to be forgotten about are the safety links. There's one small one and two of these big ones. These big safety links limit the truck frame from going farther down than it can, which keeps the truck with the locomotive in the event of a derailment. There's a large link here, and then there's a large link on the opposite corner of the bolster, and then there's one small safety link. Then a thing I forgot to mention when talking about secondary suspension, you can actually see, speaking of movement of the bolster, a block right here. When the bolster moves down, it hits that block and bottoms out, which is what limits your downward movement of the bolster. Other ancillary components. We have all of the brake rigging related components. We got the brake cylinder, the brake arm, you got the clevises into the levers. And then you got the hangers, the brake shoe head. We have this brake guide bar, which I talked about in the brake rigging video but didn't actually have. We have the brake guide itself, which just slides over it, which keeps the shoe from sliding off the wheel. You can see down here we have the slack adjuster. This one's pinned to the truck frame. And then sticking with air brakes, this right here is the air manifold. You can see it connects the two brake cylinders together on this side, and then it also jumps over to the other side of the truck, and there's one there. And you can also note there's a flexible hose that goes between that air manifold and then the piping on the locomotive. This right here is the truck cutout cock. So if we need to change a brake shoe or something like that, you can turn this, and if the locomotive had air on it, it would release all of the brakes on just this truck, which allows you to change your shoes. Alright, we're on the other side of the locomotive now. One of the reasons I actually picked this specific locomotive is because this railroad uses these. These are called flange lubricators. All this is there's a big spring in here that you can't really see, but what that spring does is push that right there, which is a block of graphite, out, and it rubs against the inside of the wheel flange. That's there to reduce wear from the flanges scraping on the rails around curves. You can see it mounts to one of the pedestal jaws, and then you can pull this pin out, release that spring to put a new block of graphite in there. Sticking with ancillary components, we also have right here the bracket, which again bolts to the underside of the pedestal tie bar. But this is the bracket for we have the sand hose and the sand nozzle, and this one actually has a dedicated nozzle tip. And this locomotive in particular has intermediate sand. You can see we are next to the fuel tank. Many of our locomotives only have sand out here on the ends of the trucks. While I'm here, the last component I want to mention is the shock absorber. This does the exact same thing as the shock absorber on your car. If you hit a bump in the rail, you don't want to get a ton of this action going on as you go down the rail. So this shock absorber, it helps to dampen those spring oscillations and provide a smoother ride. It also can help if you go around a curve or something funky. It will dampen the side-to-side movement of the car body by the same mechanism. It dampens those spring oscillations. One thing I did mention, although it turns out that this specific locomotive does not have it, some HTC trucks actually have another shock absorber that goes between the bolster and another bracket mount right here. And that, if I were to guess, became a thing because someone will know this better than I do. There were certain locomotives that EMD made that had a problem with center hunting. So as they would go down the rail, they would feel really bad, like they were shifting side to side. Those shock absorbers on the truck frame would limit that lateral movement and help to dampen those side-to-side oscillations. So yeah, that's my little spiel here about these HTC trucks. You can see we've got the air manifold, we got all the brake rigging, talked about the truck frame, the pedestal jaws and what's inside of them. We talked about a bunch of ancillary components, the shock absorbers, the sand pipes, flange lubricators. We got safety links, we've got the bolster and the secondary suspension, the primary suspension's down here. And yeah, that's our nice neat little look around of one of these HTC truck assemblies. Alright, now that we've been over truck assembly parts and you guys have got to see around an actual truck assembly, we'll go over some periodic maintenance and inspection items on truck assemblies. As far as periodic maintenance, we've actually covered most of the lubrication and wear items already in the videos on combos and brake rigging. To rattle them off, journal boxes, support bearings, and crater pans will need periodic lubrication, and brake shoes will need replacement as they wear. In terms of lubrication, the only things we haven't talked about yet are the center castings in the truck bolsters. These components are lubricated with car oil, which is added from a pipe inside of the car body of the locomotive that runs down into the center of the bolster. The rear fill pipe is typically located inside the engine room next to the air compressor, and the front one is typically either under the cab floor and can be accessed by one of the doors under the cab, or is inside the nose of the locomotive and can be accessed from the short hood. I'd also like to throw in a note here that in addition to the car oil, plenty of manufacturers also recommend that you add dry graphite when the truck is out from underneath the locomotive. It bears mentioning also that none of the other moving parts of a truck assembly should be lubricated. The jaw liners, chafing plates, movement stops for the bolster, and brake rigging should not be lubricated. Applying lubricating grease or oil to these parts will allow dust and grit from the roadbed to accumulate on the wear surfaces where it's applied, and then subsequent movement will lead to premature wear of the moving parts. Alright, that was pretty easy in terms of lubrication. Now let's get into the inspection of trucks. Starting with the truck frame, the frame should be checked for any bent, broken, or cracked members. Bends can actually be repaired by straightening if you have a fixture that's strong enough to actually do it, but I've never seen one, so I don't really know much about it. Cracks can be repaired by grinding out the cracked area and filling the crack with weld. The truck frame should also be checked for wear in areas not normally subjected to wear. For example, loose brake rigging components can cause wear of the slots through which the brake rigging moves due to having excess slop in their movement. Holes with bolts or pins should also be checked for any elongation due to wear. These holes can be repaired by either drilling the hole out and installing a bushing. They can be fixed by ring welding or plug welding and then re-drilling the hole to the proper size. These repair methods can also be used to repair mutilated threads. You can either just re-tap the threads, or likewise you can ring weld it or plug weld it, drill the hole, and then tap new threads. Speaking of threads, the truck frame should also be checked for any loose bolts or anything missing that should be there. Things like guide pin keepers and shock absorbers, and then also you'd want to check things like wear plates and cotter pins to make sure they haven't broken or sheared off. The bolster of the truck should also be checked for cracks or bends, and any wear plates on the bolster should be checked for cracks or breaks. The seal for the center casting can be checked for tears or any signs of leaking. Side bearing clearance should also be checked and should be between 1/32 and 1/4 of an inch. Note that if the side bearing clearance is approaching the minimum limit, it is likely a sign of wear in the center bearings. The center bearings can be replaced by simply removing the truck and swapping out the bearing halves.
An additional check of the center bearing wear can be made by cutting out the proper motors if applicable. It depends on the truck assembly. But cutting out motors and cutting out the brakes on a given truck and then loading the locomotive back and forth in both directions. When this happens, any movement allowed between the bolster and the car body will be taken up as the motors try to move the truck assembly around, and you can measure the amount that the truck assembly moves on the center casting. The maximum amount of movement that's allowed during this is 1/2 of an inch. The chafing plates for the bolster should be checked for a minimum thickness of 27/32 of an inch. In addition to the minimum plate thickness, the total clearance, which is obtained by adding the longitudinal distance between both ends of the bolster and their respective wear plates, must be between 1/16 of an inch and 3/8 of an inch. It's also worth noting that the chafing plates should be replaced either in side-to-side pairs or in whole truck sets, so that the variance in clearance between the two sides of the truck does not exceed 1/16 of an inch. So like you can't have one side of the truck have 1/4 of an inch of clearance and the other side of the truck have 3/8 of an inch of clearance. They need to be within 1/16 of an inch. Pedestal jaw liners should be checked for loose or missing bolts, tears, or other damage and excessive wear. The total clearance of a set of jaw liners is obtained in a similar fashion to the bolster chafing plates mentioned earlier. The sum of the gaps on both sides, meaning sides of the locomotive, of the journal box and their respective jaw liners should be between 1/8 of an inch and 3/8 of an inch. This can be obtained by adding both sides together. The maximum lateral clearance of the journal boxes from one side of the locomotive to the other is 3/4 of an inch. The maximum longitudinal, meaning front to back, clearance for a journal box movement is 1/4 of an inch. It does bear mentioning that pedestal jaw liners are designed such that replacement really shouldn't be necessary until the truck is going to be rebuilt anyway. Sticking within pedestal jaws, coil springs and spring seats should be checked for cracks or breaks, when the rubber springs in the secondary suspension should be checked for severe separation of the rubber spring material from the steel base of the spring pad. Note that the rubber spring pads can have their life shortened by exposure to large quantities of oil. Oil accumulations can be removed by washing the spring pads with a pressure washer. You can actually wash the entire truck assembly. In fact, it's recommended to keep running grit at bay. The shock absorbers and their mounting brackets should be checked for any cracked or broken parts. The condition of the rubber grommets around the mounting bolts for the shock absorber should also be checked. The shock absorber itself should not be leaking clearly formed droplets of oil. A light film of oil is permissible, but it should not be enough to accumulate into actual droplets. The last items that need checked are various smaller components. Things like the safety links to the car body, they need to be present, and the chain links should be in good position. They can't be cracked, broken, or excessively worn. Brake rigging and brake guides should be checked for proper movement and alignment to the wheels. The rigging should also be checked for warping or cracking of any of the members of the brake rigging. The air manifold to the brake cylinders should be checked for excessive corrosion or any leaks, and the flexible hoses from the air manifold to the car body should be checked for abrasion, cracks, or any other defects. The running gear of the locomotive, which includes things like the sand nozzles and brake rigging, all must be at least 2 1/2 inches above the head of the rail. Note that the only exception to this height is flexible sand nozzle tips if the locomotive is equipped with them. Alright, that was another rapid-fire slew of information, and hopefully that all made at least some amount of sense for you guys. But with that first chunk of the boring stuff out of the way, we can go on to the second chunk of the boring stuff, namely the CFR again. I know that's even more of a headache than what we just went over, but it'll be the last big section of me talking in the video, so we'll get into that. Alright, so here we are back to talking about the CFR again. As usual, we're going to be in Title 49 of the CFR, Subtitle B, Chapter 2, Part 229, Locomotive Safety Standards. Narrowing in, we're going to Subpart C, the suspension system, and that contains Parts 229.63 through 229.75. We've actually already talked about 229.73 and 229.75 already in the video on wheel sets, but we will end up coming back to 229.73 at the end to recap something that should make more sense now. So now that we know where we're at in the CFR, let's get into it. The first part we'll be going through is 49 CFR 229.63, lateral motion. A. Except as provided in paragraph B, the total uncontrolled lateral motion between the hubs of the wheels and the boxes, between the boxes and the pedestals, or both, on any pair of wheels may not exceed 1 inch on non-powered axles and friction-bearing powered axles, or 3/4 of an inch on all other powered axles. B. The total uncontrolled lateral motion may not exceed 1 1/4 inch on the center axles of 3-axle trucks. Next part, 49 CFR 229.64, plain bearings, which states, a plain bearing box shall contain visible free oil and may not be cracked to the extent that it will leak oil. Wow, that was easy. Next we have 49 CFR 229.65, spring rigging. A. Protective construction or safety hangers shall be provided to prevent spring planks, spring seats, or bolsters from dropping to the track structure in the event of a hanger or spring failure. Remember earlier in this video when I went on to the tangent about swing bolster trucks? This right here was the part that I wanted to mention that for. B. An elliptical spring may not have its top or longest leaf broken or any other 3 leaves broken except when that spring is part of a nest of 3 or more springs and none of the other springs have their top leaf or any other 3 leaves broken. An outer coil spring or saddle may not be broken, and an equalizer, hanger, bolt, gib, or pin may not be cracked or broken. A coil spring may not be fully compressed with the locomotive at rest. C. A shock absorber may not be broken or leaking clearly formed droplets of oil or other fluids. On to 49 CFR 229.67, trucks. The male center plate shall extend into the female center plate at least 3/4 of an inch. On trucks constructed to transmit tractive effort through the center plate or center pin, the male center plate shall extend into the female center plate at least 1.5 inches. Maximum lost motion in a center plate assemblage may not exceed 1/2 of an inch. Remember I mentioned that earlier about center bearings? B. Each locomotive shall have a device or securing arrangement to prevent the truck and locomotive body from separating in case of a derailment. Remember safety links? C. A truck may not have a loose tie bar or a cracked or broken center casting, motor suspension lug, equalizer, hanger, gib, or pin. A truck frame may not be broken or have a crack in a stress area that may affect its structural integrity. 49 CFR 229.69, side bearings. A. Friction side bearings with springs designed to carry weight may not have more than 25% of the springs in any one nest broken. B. Friction side bearings may not be run in contact unless designed to carry weight. Maximum clearance of side bearings may not exceed 1/4 inch on each side or a total of 1/2 inch on both sides, except where more than 2 side bearings are used under the same rigid superstructure. The clearance on one pair of side bearings under the same rigid superstructure shall not exceed 1/4 inch on each side or a total of 1/2 inch on both sides. The other side bearings under the same rigid superstructure may have 1/2 inch clearance on each side or a total of 1 inch on both sides. These clearances apply where the spread of the bearings is 50 inches or less. Where the spread is greater, the side bearing clearance may only be increased proportionally. And lastly, we have 49 CFR 229.71, clearance above top of rail. No part or appliance of a locomotive except for the wheels, flexible non-metallic sandpipe extension tips, and trip cock arms may be less than 2.5 inches above the top of the rail. Remember earlier when I talked about running gear? Alright, so that wraps up the FRA rules pertaining to truck assemblies that we haven't talked about already. Now before we finish up, let's go back and look at the first sentence of paragraph B of part 229.73.
That states, the maximum variation in the diameter between any two wheel sets in a 3-powered axle truck may not exceed 3/4 of an inch, except that when shims are used at the journal box springs to compensate for wheel diameter variation. The maximum variation may not exceed 1 1/4 inch. Remember earlier when I talked about how the shims between the coil springs in the primary suspension and the truck frame, or the coil springs in a journal box, can be changed? Those shims actually come in different thicknesses and can be changed by, if you drop the combo and the jaw liners out, you can then pull the springs off, put new shims in, and then reinstall everything. Now, that being said, in my experience, usually if we have a wheel that's too big or wheels that are too far apart in terms of size, we tend to just cut the big ones to keep the wheels all within legal limits. There also is a part of EMD's recommendations that states that the shims should be changed in order to maintain the running board and underframe height of the locomotive to a certain height above the rail. That's another thing I've never really had to deal with, so I won't pretend to know a ton about it. But yeah, that wraps up our other boring slew of information about the CFR. So that actually wraps up the last of the information I'm going to give you guys in this video. All I have left are some announcements, and then I'll close out with a short clip that I think you guys will enjoy. Alright, before we leave, I want to mention some stuff that's coming down the pipeline. For those of you who follow my weekly community posts, you'll know that I have 2 other videos in the plan. One being another locomotive walk-around, and the other being the air system overview that'll be part of my Diesel 201 series. Of those 2, I already have the walk-around recorded, so that will probably end up being the next video you guys will see. By the time this video is finished and uploaded, I'll probably started scripting for the air system video too. Something tells me that air video is going to end up being a lot longer than I'd initially anticipated, but I hope you guys will enjoy it anyway. Also, the next video of this series will likely be on couplers and maybe some other underframe components. It won't be until after those other 2 videos are done that I'll even start working on that, but it is on my roadmap, so I do have the next few videos planned out at least. And for those of you that don't know, I do post weekly in my community tab on my channel, so if you want to get a vague semblance of what's going on or progress on videos, do be sure to check them out. Anyway, everybody, that's all I have for you guys today. So I'll stop talking and I'll throw up a short clip here that I think you guys will enjoy, and then we can all get out of here. Thanks again for watching.